Aloha, Richard Halverson here. This is ITS388AL, and this is the fourth video of the semester. And today we're going to cover Chapter 3. So let me share my screen. And so I've got this is the overview page, and we are doing Chapter 3 here. We're going to assembly language fundamentals. If we click over on lessons here. This video that I'm making right now is going to be added to this page here. And this video that's already up here is a video on how to do assignment 2. So you should be looking at that. Maybe you've already seen it, but that will get you through assignment 2. So today we're going to go over the PowerPoint slides for Chapter 3. I'm going to point out to you the important part. This second link here, this is for making sure that you can have Visual Studio configured on your computer so you can assemble programs, so you can write assembly language programs. And it's important because you have to download 2 files. You have to download a zip file here which has his library, and then you also have to download this zip file here that's got a starting project. And you should start all your programs with this starting project because it's got everything configured, all set for you. You can see more of that in this video number 5, the next video. There's also a couple of videos that he made too that will help you along there. And so this week you should. We do have a quiz, a weekly quiz, something like this, true false quiz, and on Chapter 3, and we have a test. It's fill in the blank test on Chapter 3. Produces a object file, executable file, anyway, so on. So it's a fill in the blank test. So you know, as you look through here and prepare for that as you go through the chapter. So we're just gonna go through these slides here, and let's get started. Point out the important stuff. Let's go back to the beginning. Okay, here we go. So in this chapter, we're gonna basic elements of assembly language. We're gonna see very simple adding and subtracting integers. And then to get it to the point where you can execute the program, you have to assemble it, and then you have to link it, and then you can run it. And we define data in various ways. It's quite a bit different than in high-level languages. We have symbolic constants. Constants are very important. And then we're also going to talk a little bit about 64-bit programming, which is what we can do now with the processors these days. So we have to sort of understand what all these things mean. Integer constants, expressions, characters versus integers. There's reserved words are important, and identifiers, just like in high-level languages. But we have directives and instructions. They're both kind of instructions, but instructions are instructions for the microprocessor at runtime, and directives are for the assembler at assembly time or compile time. Lines in your program have labels now. As we do go-tos, and when you go to some address in the program, and so you want to label certain places. You want to know what mnemonics and operands are and how to do comments and so on. Defining integer constants, we're going to be defining them in all 3. Well, maybe not so much octal, but binary, hexadecimal, and decimal. Those are what we're going to be defining constants in those different ways. So you have to kind of remember the translation, at least maybe with some help. And you stick these letters at the end of the number, so in case it's ambiguous. R is real. R. And so examples like this is 30 base 10. This is 6A base 16, which should be 6 times 16 plus 10, whatever that is. 42, that's decimal because the default is decimal. And then this is binary, which was the 11, I think. No, 13. 13. And with text, we usually put a 0 in front of it if it starts with a letter, because otherwise you might think it's like a variable name or a label or something. For integer expressions, we have the same sort of rules as we do in other languages. Mod is designated this way, add and subtract parentheses, precedence, same thing, precedence. And expressions can be expressed like this. Precedence, you have pay attention to that. You remember that from 128. Characters and strings are defined this way: enclose a character in single quotes or double quotes. Enclose character in single quotes or double quotes. I think that's a quiz question. ASCII character is 1 byte. Enclose strings in single or double quotes. Strings in single or double quotes. Each character occupies a single byte. Each character. And if you want to embed quotes, you got to use the other one. So if you want to put some double quotes in there, you got to then you're restricted to, you must use single quotes when you define the string. Reserved words cannot be used as identifiers. None of these can be used as identifiers. See MASM reference Appendix A. So let's take a peek at that. Appendix A. So these are reserved words, register names, Microsoft Assembler. These are assembler directives. We will see some of these. We'll be using data. DDDW. You can make macros. We'll get into that at the very end of this semester. Macros, where these are assembler directives. It's like you would assemble it, or you don't, or whatever. Anyway, so it's all very interesting. Let's get back to our. Let's not take too much time here. Identifiers are not case sensitive. First character must be one of these for an identifier. Commands, these are reserved words and identifiers. Directives, commands that are recognized and acted upon by the assembler. They're directives to the assembler. They're not part of the Intel instruction set. They're used to declare code area, data area, define the memory model, when you want to declare some procedures, some subroutines, and they're not case sensitive. And different assemblers have different directives. That's assembler dependent. So the other popular assembler for assembling Intel microprocessor code is this NASM assembler, and so that the directives would be different. I mean, they're similar and they do the same sorts of things, but they might be like spelled differently or something. Instructions, however, are assembled into machine code by the assembler, and instructions are executed at runtime. And so it uses the IA32 instruction set, and an instruction contains it may contain a label if you're going to want to jump to it, if it's like the beginning of some code, or like you want to jump to it. And then there's the mnemonic, which says what the microprocessor function is, like add or subtract or whatever. And then there's usually an operand, which is like it's add this. add this to that or whatever, and then there can be a comment afterwards. And so labels they act as place markers, and so it marks the address, and usually because you want to jump to it later or you want to reference it later somehow, you want to be able to access the first point, the first data memory location of that, starting there. So you may have L1. My array may be the beginning of an array in data memory, and so on. The mnemonic is the actual instruction function directive to the microprocessor on what to do. So you're going to move some data from one place to another. You're going to add a piece of data, some memory location to some other memory location or whatever, subtract, multiply. Increment means add 1, decrement means subtract 1. And then defining the operands, it may just be like a number, a constant, after the add. Maybe some expression which is evaluated at assembly time. So it evaluates into a constant. Or it could be a register, which is like one of the registers which we saw earlier in the memory model, or a memory location. Comments you have to put comments. Constants and constant expressions are often called immediate values. The reason is because in the program code, if you're adding the number 5 to a memory if you're adding the number 5 to something, the code will actually have the value 5 immediately after the mnemonic, the op code, the operator code. Anyway, that's the history there. Comments, you gotta have comments on every line, pretty much every line. Explain the programmer's purpose, when it was written, by whom, revision information. If you're gonna do some tricky stuff, tricky stuff is good, but you gotta document it. So, if your code's got some life, or if you come back 6 months later, you want to know what the heck you were thinking when you wrote some code. And you can have lines just have comments and so on. Instruction formats. Okay, so instructions might have no operands, like the set the carry bit. It might have just one operand, like if you're going to increment the EAX register, or you're going to increment something out in the main memory, in the RAM memory. Or it can have two operands, like you're going to add the contents of ECX to EBX, or you're going to subtract the value 25, immediate value 25 from my byte, which is out in memory. Or you might tell the assembler to do this multiplication and then generate the code so it adds that to the EAX register. So let's see an example adding and subtracting integers. This is exactly the code that you're going to This is the starting project that you're going to want to download here. This is the starting project. When you download it and open it up and hook it up to the library here, then this thing will you can just run it. And you can see what the registers, and you can see memory and all that. So we're going to go through this. Are we going to go through this? Well, these are assembler directives. This model flat this defines, this is where the code segment starts. So the assembler or someone's going to find a nice code segment for you to use someplace in the physical memory, and the beginning of that code segment is going to be defined like right here, and so that would be written into the code segment register when your program loads. There's a stack segment is going to start here, and this is so you can access points on the stack segment and so on. This is the protected protected mode, memory model, and so on. That's what that's for. This defines how to return back to the operating system when your programs are done. This is your main program right here. Okay, this is your main program. This is all it is. It stores the value 5 into the EAX register, and then it adds value 6 to the EAX register, and then it's done. And but when it is done, it's not going to look like this. But here we see the EAX register has got some value in it. But this is so you're going to have this window open all the time. This looks sort of like this. So you can see, because when you're writing programs, you're going to, and especially when you're stepping through programs, you're going to want to see the manipulation of these registers to confirm stuff. There's some suggested, you know, standards that you use for writing your code. Anyway, it's just be consistent. Come up with a way and be consistent. Indentation and spacing, yeah, it's okay. Yeah, you should, because the labels have to stick out, and you know, and you want to look. So you'll see what that looks like. Required coding standards. I think I might provide a rubric. Okay, so I provide a rubric. These are my coding standards. So when you're writing this program, assignment 2, first I would take a look at this rubric, and because that's how you'll be graded. Those are my coding standards. All right, so this is the program template. Here we've got a data segment here. Data would be defined there. And this just, in the beginning, we're just going to do main, but then if we want to have subroutines or procedures or methods, we can put them down here. This is the end of the main program. So anyway, assembling, linking, and running programs. Okay, so there's an assemble, link, execute cycle. So yeah, we'll see what that is. So this is what you write. You're going to be writing a source file, and then you run it through the assembler, and that makes sure that your program in it, this your program, the part that you coded, the part that you wrote. There's any errors, syntax errors, whatever, and it produces an object file. And the object file has got, addresses in it and stuff, but it's just like addresses to, for within the code segment, addresses, within the data segment, and it's up to the linker to assign those actual addresses. So the assembler produces an object file, and it produces a listing file. And if you have any kind of errors, the listing file actually shows what the memory location of the program of assembly language instructions are, and so on. So and you may use that when you're debugging. And then there's this link library, and what the link library is it's a bunch of other methods that your source file might call. And those are going to be methods, you're going to see, those are going to be methods that our author wrote to help us, like, write to the screen, or read from the keyboard, or all those things. Those just somebody's got to write those. Those little system programs for us. They're very, I mean, we could learn how to do them from scratch, but for right now, it's just better if we use somebody else's, and then later on, we may want to write our own. But anyway, so the linker, that's why you have to have this separate linker step, because it links a bunch of object files together. and that produces an executable file. And the executable file has got, you know, it has, I guess it still does, it probably still does not have absolute addresses in it. It still doesn't have segment addresses in it because I think the loader probably does that, the operating system's loader. But the map file contains, you know, so it's got, so this thing executable file, it's got everything all collected together, and all of the code is all in one big segment, and all the data is in another big segment, and all that. And so at this point, we know exactly the size of the program and how much data size it requires. And then it's the loader that actually assigns the physical memory locations for all those segments. Listing file contains source code, addresses, object code. You can see what the machine language looks like. You can see what the segments are, and symbols, what the, you know, how the variables and so on are mapped in memory and so on. Okay, there's next different ways of defining data. There's lots of different ways of defining data, and you're probably only going to use some of them, but you're going to use a lot of them. You might, there's only maybe a few you won't use. Anyway, so we're going to go through each of these, what each of these mean. And so intrinsic data types, these are like sort of built in. We have bytes. A byte is an 8-bit, you know, it's a byte. And, you know, the microprocessor can address things in bytes. And you have unsigned bytes and signed bytes. Unsigned bytes is 0 to 255, and a signed byte is minus 128 to plus 127. That's 8 bits, though, for a byte. And we got the same thing with words, which is 16 bits. And we got the same thing with double words, which is 32 bits. And quad word is, it looks like I'm not too experienced with quad word and these T bytes. 64-bit programming. We also have these other data types for real numbers, and I think this is anyway 6, real 4, real 8, 4 bytes, 8 bytes, and 10 bytes. And so this is how you define data definition statement. This actually sets aside or allocates storage for these things. So this is going to say we may optionally have a label. There's going to be a label someplace, so because you got to have some way of referencing it. So we're going to say that this is value 1, and it's 10 bytes. So, you know, all initializers become binary data in memory, of course. So here we're going to, here's some examples of value 1 is going to be it's going to be a byte character constant. So how this works. Actually, no. This is defining a constant. It's not allocating space. It's defining a constant. So value 1 equals a byte 10. A byte value with a value 10. Yes. Yes. Okay. And so here you can, this defines 4 bytes with these values. This defines 12 bytes with these values. This is, I guess you could say it's 12 bytes long. And I'm not sure what the question mark is. Let me see. How do I want to try to stop the recording. Can I stop recording? How do I pause? All right, all the question mark means is that it's just allocates some space, but the value is going to be defined at runtime. So, all right, defining strings. A string is implemented as an array of characters for convenience. Let's see, I'm still sharing my screen and I'm still recording. All right. So this is going to allocate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 characters. It's going to have 15 bytes. The first one is addressed, this capital E is addressed by str1. And the 0 simply means that it's null terminated with the byte value of 0, and that's not any character or anything. It's just a byte with all 0, with all the bits are being 0. It just indicates that that's the end of this here string. So whatever is reading it has got to also have the convention that it's going to read until it reads a byte that's 0, which means that's the end of it. All right. To continue a single string across multiple lines, you can just put a comma there. Sure. Okay. 0D is carriage return, 0A is line feed, 0D, 0A, that's just a standard. Here is how we, this is going to define, these are other ways of using the DUP operator, which you can allocate larger chunks. So we can see that that's how this works. It sort of repeats what's in parentheses. 20 of them undefined, 20 of them stack, 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 and so on. Defining word and S-word data, same thing. Same as byte, it just, now it's word. And the others are the same, pretty much the same. Okay, this little Endian order, it's not that big a deal. It's just that the reason you want to be aware of it is because when you're debugging your program and you're looking at the memory location, the numbers are going to look funny because the numbers are in what's called little Endian order. Endian. And it turns out that Endian order is the natural. If you think about the history and how microprocessors have evolved, it just makes sense. Of course, it's going to end up being this way. But anyway, so let's say you want to store this number 12, 34, 56, 78 hex. So 8 is the lowest order and 1 is the highest order. And you want to store that in memory. Well, this is how it's stored. This is the lowest order. 78 is the lowest order. So that gets stored in the lowest order, the lowest address. And then next is 56, and that gets stored in the second address after that. And then the third one is 34, and that gets stored in the next address after that. And the highest order is 12, and that gets stored in the highest address. Okay, so, but it's going to look like this. It's going to look like 78, 56, 34, 12 when you're looking at your code. So that's all. That's all. Not that big a deal. And so here's this adds and subtracts 32-bit unsigned integers and stores the sum in a variable. So here we're defining some variable space, and these are some variables here: val1, val2, val3, and then we're defining this other word, and we're just putting a question mark because we're not going to initialize it as anything. That's where the final result is going to get written. And then so this thing takes the value that's in val1 and adds it to, and moves it to the EAX register. This adds the value that's in val2 to the EAX register. This subtracts the value that's in val3 from the EAX register. And then this stores the resulting of what's in the EAX register stores it in this final val memory location, which is right here. And then this thing is a library call to dump out the registers and display them on the screen. Something you can try that we'll try. Maybe I'll do this in the next video. Declaring uninitialized data, so you can just data segment, do it this way. Symbolic constants, this is defining constants. These are, you define these things at assembly time and then you use them at runtime. So like this, you know, it's better to use constants. It's same as using constants in high-level language. It's just good programming practice. Calculating the size of a byte array, you often use the program counter. It's called the program counter, location counter. And so here, you know, you're going along and you're defining contents of memory. And so this, in the first byte, you're going to put this. Second byte, you're going to put this. Third byte, you're going to put this. Fourth byte, you're going to put this. But this list is actually the location of the first byte. And right now, the program counter is after the fourth byte. So if you want to know the size of the array, you take the program counter and you subtract from it what this location is. And you end up with whatever the difference is. And that would be the size of this list. That would be the size of the list. Anyway, you do these kinds of tricks a lot in assembly language. Divide the total number of bytes by 2. So here you're gonna, you know, because you want to know how many words there are. So, and this gives you the number of bytes, and then you want to divide it by 2. And so this is all done at assembly time. It's done because this is defined at assembly time. As this thing is being assembled, it knows what the program counter is. It's with respect to or this would be in the data segment, with respect to the beginning of the data segment. So this is something that's done at assembly time and not at runtime. So this will calculate the size of a double array because we're using double words. And the EQU directive, define a symbol as either an integer or text expression. And this defines, and then this defines a symbol as either a text or a text expression. It's called a text macro. We'll learn a lot more about what all these are later. And then at the end, we talk about 64-bit programming, and we're not going to get too much into this, although it's very easy for you just to investigate around. We probably will sooner or later. There's a lot of other stuff we need to learn first, though. But so these tells the difference when we're setting up the directives and so on in our programs. There's a lot of stuff you got to take out some stuff basically. So this is the 64-bit version of the AddTwoSum. You notice there's some of the directives have been removed. So that's all. These are not needed. Invoke is not supported. Call instruction cannot receive arguments. Okay, so that's why you don't have the stack. All right. Summarize integer expression. You have to know what all these mean. Directives, instructions, executes at runtime, about the segments, the 3 different kinds of segments, code segment, data segment, stack segment. You want to know all these files, the source file, the listing file, the object file, map and executable files. This is a map of, we'll see all these later. And then the different data types and the different symbolic constants. And so let's see. Let me stop sharing here. The important parts of this chapter were, you know, we saw we finally saw what an assembly language program looks like. We saw, we saw what specifying literals and expressions, writing expressions, identifiers. We learned segments, how important all those are, and what it means to, there's directives that execute at assembly time but not runtime. And then the instructions themselves, those are what execute at runtime. And I wanted to show you Appendix A and B. So let me share my screen one more time here. And if we look over here, I showed you Appendix A, but Appendix B has the instruction set. And these are the instructions that that the microprocessor knows how to execute. And so when you're running, when you're writing clever code, basically you're putting these instructions together in a clever way. And so there's ANDing and there's adding and adding, and this calls a procedure. So this is it calls a label, and there's a return instruction to return from this procedure. There's the unsigned integer divide. Stack frame, this supports high-level languages. Increment instruction, integer divide, integer multiply. This is interrupt, software interrupt. This is another. It's like a jump. It's like a subroutine jump, but it stores away a bunch of stuff first. There's all different kinds of jumps on all different kinds of conditions. Any bit in the flags register, you can jump, whether it's set or clear. These are loading, loop instructions. No op is nothing. That's just dead time. This is popping from the stack, pushing it onto the stack. Repeat string, fancy string instructions. These rotate, shift. There's a difference. Subtract with borrow versus just subtract. Shifting, and so there's lots of different instructions. And so, you'll learn why they're there, and you'll probably end up using a lot of them. So anyway, that does it for chapter 3, and I recommend next you look at the video number 5, and you should be finishing the second assignment. Should be quite straightforward. Thanks for watching.